Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at how electrons organize themselves in atoms. And as we've built up so far, atoms have a series of energy levels, which can then be split into orbitals. And each of these orbitals contains only 2 electrons. However, things get a little bit messy when we're trying to talk about real systems. Because in the hydrogen atom, the only thing that dictates the energy of an orbital is going to be the principal quantum number, or n. So all orbitals with an n of 1 are going to have the same energy. Well, that's easy because there's only one orbital. But it becomes more significant when we have an n of 2 and then an n of 3. And then in order to figure out how electrons fill, you simply walk your way up. Put 2 electrons in here, 8 in here, and then 18 in the next one. However, things get a little bit messier in true multi-electronic systems, because part of the problem is as I introduce more electrons into the system, S and P orbitals no longer start sharing energies. So what ends up happening is the P orbitals energies keep going up and up and up, while the S energies start going down. And if this happens for the P, it's even more magnified in the D, that they're much more destabilized. And one of the reasons why is because of electron repulsions. As I'm putting in more electrons, well, it turns out that these p orbitals are actually pretty close to the 1s orbital. And as a result, they interfere a lot. And since the s orbital is there first, the p orbital has to get out the way. And that's more or less what ends up happening. And it becomes more magnified with the higher the L value. So one of the other issues is that as we have a lower L value, they also tend to have a significant amount of their time close to the nucleus, but out of the way of these inner core electrons. And we can see this when we look at our radial distributions. So my first electrons will always go into my first energy level, n equals 1, only one orbital there. It spends most of its time pretty close. However, something interesting happens when we go to the n equals 2, because I can have a value, an angular momentum of 0 or 1. And it is worth noting 0 is on average further out. But it has this very important feature right here, where we have a small amount of the electron that is very close to the nucleus. And it's this little extra penetration beyond the electrons in this core orbital that really lets this 2s orbital be lower in energy. So a good way to describe this is what happens is these core electrons, so the ones from lower energy levels, shield out all of the electrons further out. Because these electrons are in the way, it prevents these later orbitals from feeling the nuclear charge. And if we have a low L value, such as we see with the 2s, the 3s, and even the 3p, they're able to spend a little bit of time inside of that shielding. So what ends up happening is, again, s orbitals are very good at penetrating through this shielding effect. P orbitals, not as good as s, but still much better than d. And as a result, s orbitals are always going to have a lower energy than a p orbital of the same energy level. And p orbitals will always have a lower energy than d orbitals of the same energy level. And this helps us organize the various energy levels when we have multiple electrons. So and this gives us a predictable pattern in how to fill up our systems. Then what we can use is the fact that each orbital can contain 2 electrons. The s subshell only has the 1 orbital, so every one of our s orbitals can only contain 2 electrons. Our p subshells contain 6 electrons, and our d subshells contain 5 orbitals, each with 2 electrons. Our f orbitals contain f subshell contains 7 orbitals, each with 2 electrons. And because of this destabilization, what ends up happening is a 1s is going to be lower in energy than a 2s, then a 2p, then a 3s, then a 3p, then a 4s. Then we have to go back here to a 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. Now, this is a little bit awkward, but we can actually use it to build up a notation of where all of the electrons are in a multi-electron system. So let's say I've got arsenic. Who doesn't love arsenic? It's very poisonous, partially because your body fuses it for nitrogen. But it has 33 electrons. So the first two go into the 1s. The second two go into the 2s. The next 6 goes into the 2p. So we represent that by there are 6 electrons, superscript, in the 2p orbital. Then we have 2 electrons in the 3s, 6 electrons in the 3p, and so on and so forth, until we essentially have only 3 electrons left, and they go in the 4p orbital. And there you go. You can use this set of patterns to figure out the electronic configuration of any atom out there. However, I personally find this notation of electron filling a little bit cumbersome. And thankfully, in almost every classroom you have, there's going to be a very useful tool showing you electron configurations. This is the reason why the periodic table is so wonderful. It tells you how many electrons are in any given subshell. So it is worth noting that the first energy level is a little bit odd because it only contains the 1s electrons. So we have hydrogen and then helium. And then we move on to the next energy level. Then we have put 2 electrons in our, so if your final 2, what we call valence electrons, are in the second subshell, then like lithium and beryllium, you have 2s electrons. If your boron, carbon, nitrogen, oxygen, fluorine, or neon, you're going to have electrons. You're going to have a partially filled 2p subshell. If you're sodium or magnesium, you're going to have a partially filled 3s subshell. If you're, say, aluminum, silicon, phosphorus, sulfur, or chlorine, you're going to have all of these subshells completely filled, but a partially filled 3p. And this goes on and so forth. And you can use this as a good guideline to figure out what your electron configuration is. However, this only gets you so far. It doesn't tell you what the electron configuration is going to be if I have a partially filled subshell. And for this, we're going to need to make use of Hund's rule. So when filling out these degenerate orbitals or orbitals with the same energy, this is most important when we have a subshell or a partially filled subshell. Electrons prefer to have the same spin. And a good way to remember this is that, remember, if electrons have the same spin, they stay out of each other's way, reducing the electronic repulsion because electrons don't like each other, even if they like the nucleus. So let's go ahead and so a good way of looking at this is electrons want to travel the same way down the road. So imagine they're traveling down the highway. If you're in the same lane, you don't have to worry about collisions. If you're in opposite lanes, well, somebody might be coming your way and you're occasionally going to pass somebody. And that can be problematic. So let's go ahead and take a look at what this looks like for a set of p orbitals. So if I'm looking at my p subshell, I have 3 separate orbitals, px, py, and pz. And let's go ahead and see what happens if I have a single electron. It will fill one of these orbitals, no real preference over which one. Then another electron will go in a different orbital. Now, one of the important things is why they want to stay in orbitals is because since there is no preference, any one of these electrons may move over to a different orbital. But since this guy has an electron, has 1 electron up, it means that this second electron can only move over to an empty orbital. If they shared the same spin, this guy could occasionally sneak into the same orbital, and well, that would be very bad news. So this is a good way to make sure everybody stays out of each other's way. When we have 3 electrons, all of them will be pointed the same exact direction. Thus everybody's good. However, as soon as I put in that 4th electron, well, this 4th electron's occasionally going to be clashing with everybody else. This isn't exactly favorable. This is the reason why electrons typically like to have either full subshells, because that way everybody's lined up, or half-filled subshells, because then we don't have this pairing. But as we go to 5 electrons, we now only have 1 empty gap, which with a full subshell, everybody's happy and paired up. And maximally close, to the nucleus. Now, we need a good way to try and depict these electronic configurations, and we have several ways. There is the classic, you can literally use an arrow to draw all of the electrons. So by denoting which orbital each of these electrons are, we know the value of n, l, and m sub l. And by convention, if the arrow is pointed up, this means that we have an m sub s of plus 1/2. And so we can walk through our 2p orbitals. So if I've got, say, carbon, it's going to have a full 1s and 2s subshell. That leaves me, of my 6 electrons, 2 electrons that go into my 2p subshell, and they're all going to want to go up. Nitrogen has 1 more electron, it will go up. For oxygen, somebody's going to have to pair. I typically fill from the left. Fluorine, now I only have 1 unpaired electron, and neon, everybody's paired, everybody's happy. However, we can also denote this in what's called the SPDF notation, which is simply saying, using superscripts to tell how many electrons are in which orbital. So we have 1s orbital contains 2 electrons, 2s2, 2p2. And we can walk through for each of the individual atoms. However, it is worth noting that we do lose a little bit of information when we go from the arrow notation to the SPDF, from the diagram notation to the SPDF notation, because we lose all idea of pairing. So for that, we can use expanded SPDF notation. So this is simply a way of saying I've got 1 electron in the px orbital and 1 electron in the py, denoting that they're in different orbitals. You can apply this to all 3 orbitals, and then we start pairing the electrons up as we complete the subshell. And you can do this all the way up through d and even f orbitals. However, it is worth noting that this quickly becomes a little bit cumbersome, especially as I go to third, fourth, fifth, and even 6th row elements, because we start having a lot of orbitals present. So what we can do is use that SPDF notation. And what it says is it represents all of the core electrons that are present in the system. And a good way to look at core electrons is when you have a full SPDF notation, go ahead and look at where the last shell ends. So in this case, we're looking for where we see the previous noble gas. So carbon, our previous noble gas is helium. So we say this system has a condensed notation of helium plus two 2s electrons and 2 2p electrons. Then if we go 1 row down in the periodic table to silicon, it has a full 1s, 2s, 2p, and 3s subshells with a partially filled 3p. So if you go to your periodic table for silicon, we have a full subshell at neon, and then 6 more electrons. So we use the same condensed notation. Now, one of the very cool features that you may notice here is that the valence electrons, the essential extra electrons after the noble gas, are the exact same for carbon and silicon. And this will be true for any 2 elements that share a group. And this is the reason why the periodic table works, because if we share a group, you're going to share chemical reactivity because you share the same valence electrons. And we can go, and this carries forth as we go down to the 4th row element with germanium, who has the same notation, but even longer, because now we have 3D, a 3D subshell. And so when we introduce the D subshell, we're again go to the previous previous noble gas, in this case argon, and we reference everybody after that. So now our valence electrons include S, D, and P. However, it is worth noting, if you remember, those D electrons are pretty close to the nucleus, so they don't show a whole lot of chemical reactivity. So while they are valence electrons, they won't have the same reactivity as our S or P orbitals. So we can keep going down as we go to tin, and now we've got 2 different D orbitals, D subshells. One belongs to the core electrons, and one belongs to the valence. And if we keep going, we now go to lead, and lead gets a little bit fun because if you look at the periodic table, we've now involved the F subshell, which has those 14 electrons. And in this case, our previous element is xenon. And we go to the S subshell. And then after that, we have the F. These are called our lanthanides, and they exist in between barium and hafnium. And they kind of fill in between. And then we go to D, and then our partially filled P subshell. So again, one of the really useful things when doing these electron configurations is to make use of your periodic table. So whenever we look at a given element, your valence electrons are going to be everybody after the previous noble gas. And most of the time, you'll just have to report all of the orbitals that are occupied after that point. Then just watch out for Hund's rule and spin pairing, and you should be fine. So that brings us back to the end of this chapter. So next chapter, we're going to be focusing a little bit more in depth on this periodic table and some of the trends that we're able to now pull out of the periodic table now that we know what our electronic configurations really look like. Until then, take care.